Group 17 elements are also known as halogens. You know that these elements are the most electronegative elements among all the elements in the periodic table. Let us first study the physical properties of group 17 elements. Physical properties include physical state, color, solubility, metallic character, density, melting and boiling point, and bond dissociation energy. Let us look at each in turn. Group 17 elements appear in different physical states. For example, fluorine and chlorine are gases. Bromine is a liquid, while iodine is a solid. All these elements are diatomic in nature. Group 17 elements exhibit different colors. This is due to the fact that they absorb radiations from visible light, and the valence electrons are easily excited to higher energy levels. By absorbing different amounts of radiations, they appear in different colors, like fluorine is pale yellow, chlorine is greenish yellow, bromine reddish brown, and iodine dark violet. Of these elements, fluorine and chlorine are soluble in water. Bromine and iodine are sparingly soluble in water, but completely soluble in organic solvents like chloroform, carbon tetrachloride, carbon disulfide, etc. You know that as you move down in a group, metallic character increases. The same trend is observed for group 17 elements. Due to high ionization enthalpy values, all these elements are non-metallic in nature. The non-metallic nature decreases as we move down the group. Therefore, the last element, iodine, is a solid with a metallic luster. The densities of these elements increase regularly from fluorine to iodine, as shown in the table here. The melting and boiling points of these elements increase regularly from fluorine to iodine due to the gradual increase in their atomic size, as shown in this table. The bond dissociation energy of these elements gradually decreases from top to bottom, except for fluorine. Now let us discuss the oxidation states of group 17 elements. You know that the general electronic configuration of group 17 elements is Ns2Np5. So they have 7 electrons in their valence shell. Hence, they need only 1 electron to complete their octet and attain noble gas configuration. The octet can be achieved either by gaining 1 electron or by sharing 1 electron. As a result, the common negative oxidation state of these elements is -1. These elements exhibit +1, +3, +5, and +7 oxidation states along with -1 oxidation state as shown here. Fluorine exhibits only -1 oxidation state because it does not have d orbitals in its valence shell. It is the most electronegative element, so it cannot show any positive oxidation state. Chlorine, bromine, and iodine all exhibit 4 different oxidation states, +1, +3, +5, and +7. This is because of vacant d orbitals in their valence shells. The positive oxidation states of these elements are observed in some compounds like interhalogen compounds oxides, and oxoacids. These elements exhibits +1, +3, +5, and +7 oxidation states in interhalogen compounds of AX, AX3, AX5, and AX7 types, as shown in this table here. These elements exhibit oxidation states from +1 to +7 in their oxides, as shown in this table. Group 17 elements exhibit +1, +3, +5, and +7 oxidation states in their oxoacids like hypohalous, halous, halic, and perhalic acid series. Group 17 elements are more reactive than all other elements in the periodic table. They react with metals and non-metals to form halides. The reactivity of these elements decreases down the group. All these elements are ready to accept an electron from other elements. Hence, they are all good oxidizing agents. The oxidizing capacity of these elements decreases down the group. So, fluorine is the strongest oxidizing agent among them. Fluorine oxidizes other halide ions. In general, a halogen oxidizes higher halides to their respective halogens, as shown here. You know that the oxidizing capacity of these elements decreases down the group. This is confirmed by their reaction with water. Fluorine oxidizes water to oxygen gas, whereas chlorine and bromine produce their corresponding products, like hydrohalic and hypohalous acids. The reaction of iodine with water is non-spontaneous. In an acidic medium, iodide ions are oxidized by oxygen, as shown here. When these elements react with hydrogen, they give hydrogen halides. These hydrogen halides react with water to give hydrohalic acids. The acidic strength and bond lengths of these halides increases, and bond dissociation energy decrease from top to bottom. The melting and boiling points of these halides gradually increase from top to bottom, except for hydrogen fluoride. This is due to the high electronegativity and small atomic size of fluorine. Halogens form many oxides with oxygen. The stability of these oxides increases down the group. Fluorine forms only two oxides, OF2 and O2F2. These two are thermally stable at room temperature, and both are fluorinating agents due to the high electronegativity of fluorine. For example, O2F2 fluorinates plutonium to plutonium hexafluoride. Chlorine forms the oxides Cl2O, ClO2, Cl2O6 and Cl2O7. All these are powerful bleaching agents. ClO2 is used as a bleaching agent in the wood pulp, water purification and paper industries. Bromine forms the oxides Br2O, BrO2. All these are less stable, exist at very low temperatures, and act as powerful oxidizing agents. Iodine forms I2O4, I2O5, and I2O7. All these are solids and are insoluble in water. Among these, I2O5 is a good oxidizing agent. Halogens react with metals to give metal halides. For example, chlorine reacts with calcium to give calcium chloride. All these metal halides are ionic in nature. The ionic nature of monovalent metal halides decreases from fluorine to iodine. However, if the metal exhibits an oxidation state of more than 1, then the halide at the higher oxidation state is more covalent than the lower oxidation state. For example, SnCl4, PbCl4, SnCl5 and UF6 are more covalent than SnCl2, PbCl2, SnCl3 and UF4. Due to electronegative difference and atomic size variations, these halogens combine amongst themselves to form complexes known as interhalogen compounds of the type AX, AX3, AX5 and AX7 as shown here. Here, A is a large halogen and X is a small halogen. Let us now study the anomalous behavior of fluorine. Like all p-block elements, halogens also start from the second period in the periodic table. Fluorine shows a difference in some properties with respect to the other elements in the group. This anomalous behavior is in properties like ionization energy, electronegativity, bond dissociation energy, electrode potentials, electron gaining enthalpy, ionic and covalent radii, melting point, and boiling point, as shown in the table here. This is due to the high electronegativity, small atomic size, low bond dissociation energy, and no availability of d orbital in the valence shell. Chlorine was first prepared by Scheele in 1774 by the action of hydrochloric acid on manganese dioxide. In 1810, Davy established its elementary nature and suggested the name chlorine on account of its color. The name chlorine is derived from the Greek word chloris, which means greenish yellow. Chlorine is a greenish yellow gas. In the laboratory, chlorine is prepared by one of several methods. The first method is to heat manganese dioxide with concentrated hydrochloric acid. However, a mixture of concentrated sulfuric acid and common salt is used in place of concentrated hydrochloric acid. Another method is by the action of hydrochloric acid on bleaching powder. Chlorine can also be prepared by the action of excess hydrochloric acid on potassium permanganate. And by the action of hydrochloric acid on lead dioxide. Commercially, chlorine is manufactured by two processes. One process is the electrolytic process, in which chlorine is obtained by the electrolysis of brine in a Nelson cell. This is the cheapest method and gives the purest chlorine. Another method is Deacon's process. In this process, chlorine is obtained by the oxidation of hydrochloric acid in the presence of cuprous chloride at 723 Kelvin and 1 atmospheric pressure. Let us now look at the physical properties of chlorine. It is a greenish-yellow gas with a pungent smell. It is poisonous in nature. It has a melting point of 171.6 Kelvin and a boiling point of 239.11 Kelvin. It can be easily liquefied. It is about 2 to 5 times as heavy as air. It is fairly soluble in water. Now let us look at the chemical properties of chlorine. Chlorine dissolves in water to give a strongly smelling yellow solution called chlorine water. Chlorine water loses its yellow color on standing in sunlight due to the formation of a mixture of hydrochloric acid and hypochlorous acid. Hypochlorous acid, being unstable, decomposes and gives nascent oxygen. The nascent oxygen so formed is responsible for the oxidizing and bleaching properties of chlorine. It combines directly with all non-metals except nitrogen, oxygen and carbon. The equations for the reaction of chlorine with some non-metals like phosphorus and sulfur are shown here. Chlorine reacts readily with most metals to form their corresponding chlorides. The equations for the reaction of chlorine with some metals like sodium, iron, aluminium and zinc are shown here. It has great affinity for hydrogen. It combines with hydrogen in the presence of light with an explosion to form hydrochloric acid. It decomposes several hydrogen compounds to form hydrochloric acid. For example, it decomposes hydrogen sulfide to hydrochloric acid and sulfur. It is a good oxidizing agent. It oxidizes ferrous to ferric, sulfides to sulfates, sulfur dioxide to sulfuric acid, and iodine to iodic acid. As mentioned earlier, moist chlorine, due to the liberation of nascent oxygen, acts as a powerful bleaching agent. Its bleaching action is said to be permanent and oxidizing in character. Moist chlorine bleaches vegetable or organic matter. It forms addition compounds like sulfuryl chloride with sulfur dioxide and carbonyl chloride with carbon monoxide. It forms ammonium chloride with an excess of ammonia and the explosive nitrogen trichloride with an excess of chlorine. It forms bleaching powder with slaked lime. It forms sodium hypochlorite with cold and dilute sodium hydroxide and sodium chlorate with hot and concentrated sodium hydroxide. It reacts with saturated hydrocarbons to give substitution products and addition products with unsaturated hydrocarbons. For example, it reacts with methane in the presence of sunlight or ultraviolet light to produce chloromethane and ethene to 1,2-dichloroethane. Now let us look at the uses of chlorine. Chlorine is used as a bleaching agent in the wood pulp, cotton, and textile industries. To sterilize drinking water. As a germicide and disinfectant in swimming pools. In the extraction of gold and platinum. In the manufacture of bleaching powder, chloroform, carbon tetrachloride, dyes, drugs, rubber, etc. In the preparation of poisonous gases such as phosgene, tear gas, and mustard gas. In 1648, Glauber became the first to prepare hydrogen chloride by heating a mixture of common salt and concentrated sulfuric acid. In 1810, Davy showed that it is a compound of hydrogen and chlorine. Hydrogen chloride is prepared in the laboratory by treating sodium chloride with concentrated sulfuric acid. The reaction mixture, consisting of concentrated sulfuric acid and sodium chloride, is first heated to 420 Kelvin. Sodium bisulfate is obtained, which is insoluble and thus prevents further reaction. Hence, sodium bisulfate is mixed with more sodium chloride and further heated to a high temperature of about 823 Kelvin to give HCl gas and soluble sodium sulfate. The HCl gas is dried by passing it through concentrated sulfuric acid. Note that HCl is not dried either over phosphorus pentoxide or quicklime because it reacts with them both, as shown here. Let us now study the properties of hydrogen chloride. Hydrogen chloride is a colorless gas with a pungent odor. It liquefies to a colorless liquid at 189 Kelvin and freezes to a white solid at 159 Kelvin. It is highly soluble in water. At room temperature, 1 volume of water dissolves 452 volumes of hydrogen chloride. An aqueous solution of hydrogen chloride is called hydrochloric acid. An aqueous solution of hydrogen chloride undergoes ionization to produce hydronium ions and chloride ions. The ionization of hydrochloric acid, along with the Ka value, is shown here. The larger value of the dissociation constant indicates that hydrochloric acid is a strong acid. In other words, on account of its ability to dissociate almost 100% to produce hydronium ions, it is considered a strong acid. Hydrochloric acid reacts with metals and alkalis to form chlorides. For example, it reacts with zinc to form zinc chloride and with sodium hydroxide to form sodium chloride. Note that hydrochloric acid reacts with iron to form ferrous chloride and not ferric chloride. This is because the hydrogen liberated prevents the formation of ferric chloride. Hydrochloric acid reacts with ammonia to form dense white fumes of ammonium chloride. You know that noble metals such as gold and platinum are insoluble even in hot and concentrated nitric acid. However, noble metals dissolve in a concentrated solution of nitric acid and hydrochloric acid taken in the ratio of 1:3. This solution is called aqua regia. Aqua regia produces nascent chlorine, due to which noble metals dissolve in it. The nascent chlorine attacks these noble metals to form chlorides, which eventually form soluble complexes on reacting with hydrochloric acid, as shown in these equations. Hydrochloric acid decomposes salts of weaker acids, such as sodium carbonate, sodium bicarbonate, and sodium sulfite. You can see from the balanced chemical equations that hydrochloric acid decomposes sodium carbonate and sodium bicarbonate to sodium chloride, carbon dioxide, and water, while it decomposes sodium sulfite to sodium chloride, sulfur dioxide, and water. Let us now look at the uses of the aqueous solution of hydrogen chloride or hydrochloric acid. It is used in the manufacture of chlorine and chlorides like ammonium chloride. It is also used in the manufacture of glucose from cornstarch. It is used for extracting glue from bones and purifying bone black. It is used as a laboratory reagent and in medicines. A saturated solution of zinc chloride in dilute hydrochloric acid is used to remove the impurities on a metal surface before soldering or electroplating. Halogens usually form 4 series of oxo acids, namely hypohalous acids, halous acids, halic acids and perhalic acids, which are represented by the general formulae HOX, HOXO, HOXO2 and HOXO3, as shown here. X represents the halogen, which may be fluorine, chlorine, bromine or iodine. Most oxo acids of halogens cannot be isolated in pure state. They are stable in their aqueous solutions or in the form of their salts. The table here lists the formulae and oxidation states of the 4 series of oxo acids of each halogen. Note the oxidation state of the central atom, fluorine, chlorine, bromine, and iodine in each oxo acid. Examine the structures of the oxo acids given here. Let us now discuss some important features of the structures of the oxo acids of halogens. In all of these oxo acids, the central halogen atom is sp3 hybridized. One XOH bond is essentially present in every oxo acid. In most of these oxo acids, X double bond O bonds are present. The double bond present in an oxo acid between the central halogen atom and oxygen is d-pi, p-pi in nature. The first series, that is, hypohalous acids, include hypofluorous acid, hypochlorous acid, hypobromous acid, and hypoiodous acid. The halogen has the oxidation state of +1 in hypohalous acids. The respective hypohalite ions have a linear shape owing to the presence of 3 lone pairs of electrons on the central halogen atom, as shown here. Note that the hypohalous acids, being less stable, tend to form halic acids. Note that the only oxo acid of fluorine is hypofluorous acid. No higher oxo acid of fluorine is known due to the absence of d orbitals in the fluorine atom. The second series, that is, halous acids, includes only chlorous acid. The chlorine in chlorous acid has the oxidation state of +3. The chlorite ion has a V shape owing to the presence of 2 lone pairs on the central chlorine atom. The third series, that is, halic acids, includes chloric acid, bromic acid, and iodic acid. The halogen has the oxidation state of +5 in these oxo acids. The respective halate ions are pyramidal in shape owing to the presence of a lone pair of electrons on the central halogen atom, as shown here. The fourth series, that is, perhalic acids, includes perchloric acid, perbromic acid, and periodic acid. the oxidation state of the halogen in these oxoacids is +7. The shape of the perhalate ion is tetrahedral. In any series of oxoacids of halogens, the first member possesses high acidic strength. This is due to the high electronegativity and small size of the respective halogens, fluorine in the hypohalous acid series and chlorine in the other series of oxoacids. For example, among perhalic acids, perchloric acid has high acidic strength. As chlorine is more electronegative than bromine or iodine, the shared electron pair lies relatively nearer to chlorine in a CLO bond than bromine in a BRO bond or iodine in an IO bond. As a consequence, the OH bond becomes much weaker in case of perchloric acid, thereby facilitating the release of a proton readily. Let us now see how the acidic strength varies for the oxoacids having the same central halogen atom. The acidic strength of an oxoacid increases with an increase in the oxidation number of the halogen. For example, among the 4 oxoacids of chlorine, the acidic strength increases markedly from hypochlorous acid to perchloric acid. Hence, we can conclude that perchloric acid is the strongest acid among all the oxoacids of halogens. Interhalogen compounds are the derivatives of halogens. Let us see the definition for interhalogen compounds. Compounds containing 2 different types of halogens are called interhalogen compounds. Example: chlorine monofluoride, bromine trifluoride, iodine pentafluoride, iodine heptafluoride, etc. Let us first discuss the types of interhalogen compounds. Depending on the number of atoms in the molecule, interhalogens are classified into 4 types. They are AX, AX3, AX5, AX7, where A is larger or less electronegative halogen and X is a smaller or more electronegative halogen. Note that in these types of molecules, the number of atoms per molecule are 2, 4, 6, and 8 respectively. Number of atoms in a molecule can be known with the radius ratio. Radius ratio is equal to radius of larger halogen atom upon radius of smaller halogen atom. As the radius ratio increases, the number of atoms per molecule also increases. So, among interhalogen compounds, iodine heptafluoride has largest number of atoms per molecule as it has highest radius ratio. Let us now discuss the preparations of interhalogen compounds. These compounds are prepared by two methods. They are by direct combination of halogens and by reaction of halogens with lower interhalogen compounds. In the first method, different halogen molecules react directly to form interhalogen compound. For example, equal volumes of chlorine and fluorine combine at 473 Kelvin to form chlorine monofluoride. In the second method, a halogen molecule reacts with a lower interhalogen to form a new interhalogen compound. For example, fluorine reacts with iodine pentafluoride at 543 Kelvin to form iodine heptafluoride. Now let us discuss some of the physical properties of interhalogen compounds. Interhalogen compounds exist in gaseous state, liquid state, or solid state. Most of these compounds are volatile solids or liquids at 298 Kelvin, while remaining are gases. For example, chlorine monofluoride is gas, while bromine trifluoride and iodine trifluoride are existing in liquid and solid state respectively. All these compounds are covalent in nature due to less electronegativity difference between bonded atoms. Example, chlorine monofluoride, bromine trifluoride, iodine heptafluoride are covalent. All these compounds are dimagnetic in nature, as they have only lone pairs and bond pairs. Interhalogen compounds are more reactive than constituent halogens, except fluorine. This is because AX bond in interhalogens is weaker than XX bond in halogens, except FF bond. The molecular formula, physical state, color and shapes of these compounds are shown in the table here. From this table, note that for AX compounds, like chlorine monofluoride is a colorless gas, bromine monofluoride is pale brown gas, while iodine monofluoride is unstable. Bromine monochloride is a gas, while iodine monochloride is ruby red solid, while iodine monobromide is black solid. Among AX3 type, chlorine trifluoride is a colorless gas and bromine trifluoride is yellow-green liquid, while iodine trifluoride and iodine trichloride are yellow and orange solids. Among AX5 type, iodine pentafluoride is colorless gas, but solid below 77 Kelvin, while chlorine and bromine pentafluorides are colorless liquids. Among AX7 type, the only molecule existing of this type is iodine heptafluoride, which is colorless gas. Structure of these different types of interhalogens are different from one another. The structures of these molecules are explained using VSEPR theory. Let us now deduce the structure of chlorine trifluoride. In chlorine trifluoride, the central atom chlorine has 7 electrons in the valence shell. 3 of these will form 3 bond pairs with 3 fluorine atoms, leaving 4 electrons. So, according to VSEPR theory, these will occupy corners of trigonal bipyramid. The lone pairs will occupy the equatorial positions, while bond pairs will occupy the other 3 positions. To minimize the lone pair repulsions, the axial bond pairs will bend towards the equatorial positions. Hence, its shape is bent T-shape. In iodine pentafluoride, the central atom has 5 bond pairs and 1 lone pair, hence, shape is square pyramidal. The structure of this molecule is shown here. In iodine heptafluoride, the central atom has 7 bond pairs, so it has pentagonal bipyramidal shape. On hydrolysis, they form a halide ion from smaller halogen X and a hypohalite ion, halite ion, halate ion, and perhalate ion from larger halogen A. For example, interhalogen AX react with water to form hydrogen halide HX and hypohalite HOA as shown in the equation. These interhalogen compounds have many applications, such as halogenating agents. Example, tungsten reacts with chlorine monofluoride to form tungsten hexafluoride, releasing chlorine gas as shown in the equation. As non-aqueous solvents, electrolytic solvent. Production of uranium hexafluoride for enrichment of uranium. Example, uranium reacts with chlorine trifluoride at 50 to 90 degrees Celsius to form uranium hexafluoride and chlorine monofluoride as shown here. The elements in group 18 are helium, neon, argon, krypton, xenon, and radon. These elements are collectively referred to as noble gases. The term noble gases implies that these elements tend to be chemically inert or unreactive, just as noble metals that show reluctance to react under normal conditions. However, compounds of xenon, such as fluorides, oxides and oxyfluorides, and fluorides of krypton are known. These compounds can be prepared only under drastic conditions at high pressure and temperature. Now let's look at the electronic configuration of the group 18 elements. The general valence shell electronic configuration of these elements is Ns2 NP6, except for helium. Note that the electronic configuration of helium is 1s2. Although helium does not possess an octet, it resembles other elements of the 18th group. The electronic configuration of these elements are listed in the table here. You can see from the table that the NP subshell is completely filled in all the elements. Due to the duplet or octet configuration in their valence shells, the elements of this group are highly stable. In other words, as these elements have closed shell structures, they have less or no tendency to form compounds. As these elements do not have a tendency to lose, gain, or share electrons with atoms of other elements, their valency is 0. The stability or inert nature of these elements is further attributed to the symmetrical arrangement of their electrons. Let's now discuss the occurrence of these elements. Owing to their inert nature, all the noble gases occur in free state. All the noble gases, helium, neon, argon, krypton and xenon, except radon, occur in the atmosphere. Note the percentage abundance of these elements listed here in the table. These gases make up approximately 1% by volume of the atmosphere, in which argon alone constitutes 0.93%. As argon is quite abundant in air, it can be obtained from liquid air by fractional distillation. On the contrary, since helium is scanty in the atmosphere, its recovery from air would become highly expensive. Natural gas deposits are the most important commercial and economical source of helium. Helium is also found in the minerals of radioactive elements, uranium and thorium, such as clevite, monazite and pitchblende. These minerals give off helium gas on being chemically treated. Certain water springs contain helium, neon and argon in the form of dissolved gases. Radon is a radioactive substance that is produced by the decay of radium and thorium minerals. Let us now discuss the trends in some of the atomic properties of the group 18 elements. The table here lists the trends in some of the atomic properties of the group 18 elements. The atomic radii increase on descending the group with an increase in the atomic number. This is because of the addition of a new shell at each successive element on descending the group. Talking again about their electronic configuration, you know that these elements have closed shell structures. which render them stable. As a consequence, these elements have very high ionization potentials. In other words, the removal of electrons from the valence shell is very difficult. However, you can see from the table that ionization enthalpies decrease gradually on descending the group with an increase in the atomic size. Note that the ionization enthalpy of a noble gas is the highest among the elements of the same period. Again, because the elements of group 18 have stable electronic configurations, they do not have a tendency to accept electrons. Hence, they have very high positive values of electron gain enthalpy. Let us begin our study with the physical properties. You know that the elements of group 18 have closed shell structures, because of which they have no tendency to form compounds under normal conditions. Owing to their inert nature, these elements exist in free state as monoatomic gases. These elements are colorless, tasteless, and odorless gases. They are sparingly soluble in water. The forces holding the atoms together are weak van der Waals forces of attraction, which is evident from the very low values of enthalpy of vaporization as shown here in the table. The weak van der Waals forces of attraction are also called London dispersion forces. The magnitude of van der Waals forces increases on moving down the group with an increase in the polarizability of the atoms. You can see from the table that the melting and boiling points of these elements are very low. This is, in fact, due to the weak van der Waals forces of attraction or weak dispersion forces. However, the melting and boiling points increase on descending the group with an increase in the magnitude of the van der Waals forces of attraction. In other words, more energy is required to overcome the forces between the atoms with an increase in the atomic size or with an increase in the diffusion of the electron cloud. Further, due to the weak van der Waals forces, noble gases can be liquefied at very low temperatures. With an increase in the magnitude of the van der Waals forces down the group, the ease of liquefaction of noble gases also increases. Note that helium has the lowest boiling point among all the elements in group 18. Moreover, it has the lowest boiling point of any element, just 4.2 Kelvin. Liquid helium finds use in cryoscopy to obtain the very low temperatures required for superconductivity. Helium has the unusual property of being able to diffuse through glass, rubber, and plastic, which are commonly used as laboratory materials. Let us now discuss the chemical properties of these elements. You know that the inertness of these elements to chemical reactivity is attributed to their stable electronic configuration, high ionization enthalpy, and higher positive electron gain enthalpy. Before 1962, several attempts made by chemists to force these elements to react and form compounds were unsuccessful. In 1962, Neil Bartlett predicted that xenon should react with platinum hexafluoride just as dioxygen because the first ionization energies of both oxygen and xenon are nearly the same. His efforts were successful. He was the first to prepare a compound of xenon called xenon hexafluoridoplatinate 5. Later, many compounds of xenon were synthesized, including fluorides, oxides, and oxyfluorides. The data in the table for ionization enthalpy here shows that the chemical activity of group 18 elements increases with the decrease in the ionization enthalpy on descending the group. The ionization enthalpies of helium, neon, and argon are too high for them to form compounds. On the other hand, krypton forms only krypton difluoride, since its ionization enthalpy is slightly higher than that of xenon. Even though radon has less ionization enthalpy than xenon, it forms only some compounds like radon difluoride and some complexes. Since radon has no stable isotopes. However, xenon forms a markedly greater number of compounds. You know that in 1962, Neil Bartlett predicted that xenon should react with platinum hexafluoride just as dioxygen, because the first ionization energies of both oxygen and xenon are nearly the same. His efforts were successful. He was the first to prepare a compound of xenon called xenon hexafluoridoplatinate 5. Later, many compounds of xenon were synthesized, including fluorides, oxides, and oxyfluorides. Let us first discuss the methods to prepare xenon-fluorine compounds. Xenon directly reacts with fluorine to form a binary fluoride, which may be xenon difluoride xenon tetrafluoride or xenon hexafluoride. The product depends on the ratio in which xenon and fluorine react. When a mixture of xenon and fluorine in the ratio of 2:1 is heated at 673 Kelvin in a sealed nickel vessel at 1 bar pressure, xenon difluoride is formed. Xenon tetrafluoride is obtained when a mixture of xenon and fluorine in the ratio 1:5 is heated at 873 Kelvin in a sealed nickel vessel at 7 bar pressure. Xenon hexafluoride is obtained when a mixture of xenon and fluorine in the ratio 1:20 is heated at 573 Kelvin in a sealed nickel vessel at 60 to 70 bar pressure. Xenon hexafluoride can also be obtained by the reaction of xenon tetrafluoride and dioxygen difluoride at 143 Kelvin. Let us now take a quick look at the structural aspects of the fluorides of xenon. The central atom, xenon, in xenon difluoride undergoes sp3 dehybridization. Xenon difluoride has 5 electron pairs. Of these, 3 are lone pairs and 2 are bond pairs. The structure of xenon difluoride is linear owing to the presence of the 3 lone pairs of electrons on the central xenon atom, as shown here. The central atom, xenon, in xenon tetrafluoride undergoes sp3 d2 hybridization. Xenon tetrafluoride has 6 electron pairs. Of these, 4 are bond pairs and 2 are lone pairs. The structure of xenon tetrafluoride is square planar owing to the presence of the 2 lone pairs of electrons on the central xenon atom, as shown here. The central atom, xenon, in xenon hexafluoride undergoes sp3 d3 hybridization. Xenon hexafluoride has 7 electron pairs. Of these, 6 are bond pairs and 1 is a lone pair. The structure of xenon hexafluoride is distorted octahedral owing to the presence of the single lone pair of electrons on the central xenon atom, as shown here. Finally, let us study the properties of xenon fluorides. All the fluorides of xenon are white crystalline solids. They are sublimable at room temperature. They are strong oxidizing and fluorinating agents. For example, xenon difluoride oxidizes chloride ions to chlorine, while xenon tetrafluoride oxidizes iodide ions to iodine, as shown here. Similarly, xenon tetrafluoride fluorinates platinum and sulfur tetrafluoride, as shown by these chemical equations. Xenon tetrafluoride and xenon hexafluoride react violently with water, while xenon difluoride reacts slowly with water. You can see from the equations that the products of the slow hydrolysis of xenon difluoride are xenon, hydrofluoric acid, and dioxygen, while xenon tetrafluoride and xenon hexafluoride undergo hydrolysis to give xenon trioxide as the main product. Xenon fluorides form complexes called xenon fluoride complexes. They form complexes with covalent pentafluorides, such as phosphorus pentafluoride, antimony pentafluoride, and arsenic pentafluoride. Note that xenon fluorides act as fluoride donors. Xenon difluoride reacts with phosphorus pentafluoride, while xenon tetrafluoride reacts with antimony pentafluoride to form cationic species, as shown here by the chemical equations. On the other hand, xenon hexafluoride can also act as a fluoride acceptor with rubidium fluoride. You know that in 1962, Neil Bartlett predicted that xenon should react with platinum hexafluoride just as dioxygen, because the first ionization energies of both oxygen and xenon are nearly the same. His efforts were successful. He was the first to prepare a compound of xenon called xenon hexafluoridoplatinate 5. Later, many compounds of xenon were synthesized, including fluorides, oxides, and oxyfluorides. Let us first discuss the methods to prepare xenon-fluorine compounds. Xenon directly reacts with fluorine to form a binary fluoride, which may be xenon difluoride, xenon tetrafluoride, or xenon hexafluoride. The product depends on the ratio in which xenon and fluorine react. When a mixture of xenon and fluorine in the ratio of 2:1 is heated at 673 Kelvin in a sealed nickel vessel at 1 bar pressure, xenon difluoride is formed. Xenon tetrafluoride is obtained when a mixture of xenon and fluorine in the ratio 1:5 is heated at 873 Kelvin in a sealed nickel vessel at 7 bar pressure. Xenon hexafluoride is obtained when a mixture of xenon and fluorine in the ratio 1:20 is heated at 573 Kelvin in a sealed nickel vessel at 60 to 70 bar pressure. Xenon hexafluoride can also be obtained by the reaction of xenon tetrafluoride and dioxygen difluoride at 143 Kelvin. Let us now take a quick look at the structural aspects of the fluorides of xenon. The central atom, xenon, in xenon difluoride undergoes sp3 dehybridization. Xenon difluoride has 5 electron pairs. Of these, 3 are lone pairs and 2 are bond pairs. The structure of xenon difluoride is linear owing to the presence of the 3 lone pairs of electrons on the central xenon atom, as shown here. The central atom, xenon, in xenon tetrafluoride undergoes sp3 d2 hybridization. Xenon tetrafluoride has 6 electron pairs. Of these, 4 are bond pairs and 2 are lone pairs. The structure of xenon tetrafluoride is square planar owing to the presence of the two lone pairs of electrons on the central xenon atom, as shown here. The central atom, xenon, in xenon hexafluoride, undergoes sp3d3 hybridization. Xenon hexafluoride has 7 electron pairs. Of these, 6 are bond pairs and 1 is a lone pair. The structure of xenon hexafluoride is distorted octahedral, owing to the presence of the single lone pair of electrons on the central xenon atom, as shown here. Finally, let us study the properties of xenon fluorides. All the fluorides of xenon are white crystalline solids. They are sublimable at room temperature. They are strong oxidizing and fluorinating agents. For example, xenon difluoride oxidizes chloride ions to chlorine, while xenon tetrafluoride oxidizes iodide ions to iodine, as shown here. Similarly, xenon tetrafluoride fluorinates platinum and sulfur tetrafluoride, as shown by these chemical equations. Xenon tetrafluoride and xenon hexafluoride react violently with water, while xenon difluoride reacts slowly with water. You can see from the equations that the products of the slow hydrolysis of xenon difluoride are xenon, hydrofluoric acid, and dioxygen, while xenon tetrafluoride and xenon hexafluoride undergo hydrolysis to give xenon trioxide as the main product. Xenon fluorides form complexes called xenon fluoride complexes. They form complexes with covalent pentafluorides such as phosphorus pentafluoride, antimony pentafluoride, and arsenic pentafluoride. Note that xenon fluorides act as fluoride donors. Xenon difluoride reacts with phosphorus pentafluoride, while xenon tetrafluoride reacts with antimony pentafluoride to form cationic species, as shown here by the chemical equations. On the other hand, xenon hexafluoride can also act as a fluoride acceptor with rubidium fluoride. Let us first discuss the methods to prepare xenon oxides and xenon oxyfluorides. Xenon tetrafluoride and xenon hexafluoride undergo complete hydrolysis to give xenon trioxide, as shown in these chemical equations. On the other hand, xenon hexafluoride undergoes partial hydrolysis to give oxyfluorides such as xenon oxytetrafluoride or xenon dioxydifluoride, as shown in the equations here. Try to answer this question on your own before looking at the answer. Is the hydrolysis of xenon hexafluoride a redox reaction? No. As there is no change in the oxidation state of any element in the reactants and products, the hydrolysis of xenon hexafluoride is not a redox reaction. Let us now take a quick look at the structural aspects of some of the oxides and oxyfluorides of xenon. The central atom, xenon, in xenon trioxide undergoes sp3 hybridization. Xenon trioxide has 7 electron pairs. Of these, 6 are bond pairs and 1 is a lone pair. Note that there are 3 d-pi-p-pi bonds in the molecule. The structure of xenon trioxide is pyramidal, owing to the presence of a lone pair of electrons on the central xenon atom, as shown here. The central atom in xenon oxytetrafluoride undergoes sp3d2 hybridization. Xenon oxytetrafluoride has 7 electron pairs. Of these, 6 are bond pairs and 1 is a lone pair. Note that there is 1 d-pi-p-pi bond in the molecule. The structure of xenon oxytetrafluoride is square pyramidal owing to the presence of a lone pair of electrons on the central xenon atom, as shown here. The central atom in xenon dioxydifluoride undergoes sp3d hybridization. Xenon dioxydifluoride has 7 electron pairs. Of these, 6 are bond pairs and 1 is a lone pair. Note that there are 2 d-pi-p-pi bonds in the molecule. The structure of xenon dioxydifluoride is seesaw owing to the presence of a lone pair of electrons on the central xenon atom, as shown here. Finally, let us study the physical properties of xenon trioxide and xenon oxytetrafluoride. Xenon trioxide is a colorless, explosive and hygroscopic crystalline solid, while xenon oxytetrafluoride is a colorless liquid. Let us begin our study with the uses of helium. Helium is not inflammable and has a very low density. That is why it is used to fill weather balloons and airships. Note that it is less dense than air. 1 cubic meter of helium gas can lift 1 kg. You know that helium has the lowest boiling point among all the elements in group 18. Moreover, it has the lowest boiling point of any element, just 4.2 Kelvin. Hence, liquid helium is used as a cryogenic agent to perform experiments at very low temperatures. Liquid helium finds use in cryoscopy to obtain the very low temperatures required for superconductivity. Liquid helium is used to cool the superconducting magnets used in nuclear magnetic resonance spectrometers. Liquid helium is also used in the medical field to cool the superconducting magnets that are essential components of magnetic resonance imaging (MRI) systems. You know that MRI systems are used for clinical diagnosis. It is used as the cooling gas in gas-cooled nuclear reactors and as a flow gas in gas-liquid chromatography. Helium is used to dilute dioxygen in the cylinders carried by sea divers. This is because it is only slightly soluble in blood even at the high pressures that divers encounter deep in the sea. Let us now discuss the uses of neon, argon, krypton and xenon. Neon is used in small amounts in discharge tubes and fluorescent bulbs that give the familiar red-orange glow of neon signs. Hence, these tubes are used extensively in advertisement displays. Neon bulbs are also used in botanical gardens and greenhouses as neon stimulates the growth of plants. Argon is widely used to provide an inert atmosphere in laboratory apparatus and for metallurgical processes, such as in welding stainless steel, aluminium and magnesium. Also, it is used to fill electric light bulbs to prolong the life of the filament. Krypton is used in filament lamps and discharge tubes, while xenon is used in discharge tubes to produce the high-speed flash required for photography. Radon finds use in radiotherapy for the treatment of cancer.